This lecture will introduce the simple gas laws. There are additional gas laws that are a little bit more complex that we'll go over after this lecture. First one I'm going to talk about is called Boyles Law. And Boyles Law describes the relationship between pressure and volume. And basically what it is saying is that the product of the pressure of any particular gas times its volume is a constant. Okay, so that tells us there's an inverse relationship between pressure and volume. As pressure goes up, volume must go down, or vice versa. And that's probably intuitive for you, right? So if you have gas and you compress it to a smaller volume, the pressure is going to go up. So you can kind of intuit that too. And the Boyles Law equation is very handy for us if we have a gas and we can quickly calculate what will happen to the volume, for example, if we change the pressure or vice versa. And what I think is really cool is that we can use Boyles Law to explain how our lungs work in breathing. So when you inhale, what's actually happening is your diaphragm allows your lungs to expand. Okay, so you're not initiating breathing process by sucking in air. There's something that happens before that, and that is that your lungs expand. And so what happens to the pressure inside? When the volume increases, right, the pressure inside your lungs for a short moment goes down because of the increased volume. So you've created somewhat of a vacuum in your lungs for just a split instant because the pressure went down. Well, what happens when you start creating a vacuum? More gases get sucked in, more air gets sucked in to fill up that vacuum. And so instantly following an inhalation is the air sucking in through our mouth or nose, whatever, to equalize the pressure between outside and inside. I just thought that was pretty cool. On a molecular level, let's look at Boyles Law. So on a macroscopic level, we can say, okay, pressure goes up, volume goes down. But on a molecular level, let's look at what happens here. So if we have gas contained in a sealed container and we compress the volume, okay, so Boyles Law says as volume goes down, pressure goes up, right? So how do we explain that on a molecular level? Well, if you remember from our Introduction to Gas lecture, gas pressure is caused by collisions of the gas particles on the container walls. So when we decrease volume, we have more collisions, right? The gas particles are enclosed in a smaller space, and so there are more collisions. More collisions means higher pressure. So on a molecular level, that explains Boyles Law. Any inverse relationship, if you graph it, is going to look like this: a downward curving downward curving slope. So here's a typical graph of a Boyles Law relationship showing that as volume decreases, pressure increases, or vice versa. Okay, so let's look at a sample problem. A balloon is partly inflated, okay, so with 5 liters of helium. So let's write Boyles Law here and let's start labeling. Because it's really simple math, and if there's going to be an issue, it's probably getting mixed up in labeling some of the given information by the wrong value. So let's call this volume 1. That's the initial volume. Okay. At the initial atmospheric pressure is 1 atmosphere, so we're going to call that P1. Now, please remember that STP conditions, or sometimes it's just called normal atmospheric conditions. So in the future, you're going to have to know that means 1 atmosphere. Okay, in this case, the problem told you, but kind of tuck that in your brain. Okay, so what's going to happen? The balloon rises, and at higher altitudes, we know the pressure is lower. So the question is then, what is going to be V2? What's going to be the new volume when the pressure is lower? So now you just simply plug into Boyles Law. All right, so P1 we said was 1 atmosphere. V1 was 5 liters. P2 is 0.83 atmospheres. Also make sure that your units on both sides of the equation match. Some problems will give atmosphere for P1 and millimeters of mercury for P2, so just be careful of that. And then V2 is what we're solving for. Okay, and then rearranging it to solve for V2, we get that the volume at the higher altitude is 6 liter. So use your common sense in these gas law problems to make sure you didn't make a silly math error. Does it make sense? Okay, so the initial volume was 5 liters. Does it make sense that the volume increased? The volume of the balloon increased. Does that make sense? Well, let's just look mathematically. We know there's an inverse relationship, right? So we have decreased volume, we have decreased pressure, which means that volume should go up because they're inversely, and it did. Volume went up. So that intuitively makes sense. The next simple gas law we're going to go over is called Charles' Law. Charles' Law relates volume and temperature. So you'll notice each of these simple gas law picks 2 of the 4 variables we work with. I don't know if you remember, but in the intro lecture, the variables that affect gases are pressure, temperature, volume, and number of moles. So each of these laws pick 2 of those variables to ask what is the relationship between these 2 variables given that the other 2 variables are held constant. So Charles' Law again, what's the relationship between volume and temperature? These 2 variables are directly related. So from a mathematical point of view, the ratio of the 2 is a constant. And what that tells us is that if temperature goes up, volume must also go up. If temperature goes up, volume must also go up. That's the only way to have that ratio remain a constant. And intuitively, does that make sense? It does. I love this example here. Okay, so you put a balloon over a container, and if you start heating up that container of gas, okay, the gas is going to expand, right? You give it more kinetic energy, it's going to start trying to spread out, and so your volume is going to increase. So higher temperature, higher volume. Now, all of these simple gas laws are assuming the other variables are held constant. So in this case, we're not talking about pressure and we're not talking about moles. So what we say is that the variables not in the equation are held constant. Because once you change more than one variable, then it's a whole new ballgame. So here's the form of Charles' Law that are useful to us to introduce initial volume and temperature and then say, okay, if we change one of them, what's going to happen to the other? And as with any direct relationship, if 2 variables are directly proportional and you plot them, you are going to get a linear relationship showing that they are direct. Oh, Charles' Law. Okay, so I made a point to tell you that in all gas laws, well, even when you're talking about gases, period, your temperatures should be in Kelvin, not Celsius. And I don't know if you've heard about absolute zero before, but that's 0 Kelvin, okay, which is minus 273 degrees Celsius. And that's the temperature at which scientists theorize that all motion will stop. And we have never gotten to absolute zero. We've gotten very, very close to it with some supermagnets. But so this is a theory, but it's pretty well supported. And if you take any gas and you start, this should be temperature down here, and you start reducing the temperature, so the Kelvin scale is here. Okay, just as expected, according to Charles' Law, as you decrease temperature, volume will also go down, also decrease. And of course, as I said, we have never reached absolute zero, but we can extrapolate this line that says, okay, if and when we ever reach absolute 0 Kelvin, then the volume should go to 0. So yes, kind of theoretically impossible. But that's where the whole concept of absolute 0 came from. All right, so the molecular view of Charles' Law, again, it's intuitive. So if you have a balloon, you blow it up normal, right? If you put that balloon in your freezer or in ice water, what's going to happen? It's going to shrink, okay? So that tells us, again, as temperature goes down, volume's going to go down, assuming all the other variables are constant. And from a molecular point of view, why is that, okay? Well, what happens when you lower temperature? That means lower kinetic energy, less motion, right? What does less kinetic energy and less motion mean for gas particles? Now remember what causes pressure from gases. It's collisions with the container wall. So if these particles have less kinetic energy, they're going to be less frequent collisions, okay? And if the volume, if it's a flexible volume, if it's a material that can shrink and expand, it's going to, okay? If there's less pressure on it, it's going to automatically shrink down because it is pressure that keeps a balloon inflated, right? So if you reduce the pressure. All right, so now boiling water, same type of thing, right? When you heat something up, you're giving more kinetic energy to the gas particles inside. They're going to collide more frequently with the container wall, and since a balloon is a flexible container wall, it's going to expand to accommodate the higher force. Avogadro's law, the third simple gas law we're going to talk about, relates volume of a gas to the number of moles of the gas. And so the relationship between those two is direct again, okay, direct relationship, linear graph. And the useful Avogadro's law, which I see I don't have here, would be this. The ratio of volume to moles is, since it's a constant, we can set this up and then actually calculate the effect of changing the moles or changing the volume for a particular gas. Now, I don't know if you remember, it might have been the second slide or something on the introductory PowerPoint when I went over, I said one of the unique properties of gas is that equal volumes of gases contain equal molecules, equal number of molecules, regardless of what the gas is. And then I reminded you that's not true for liquids and solids, because if I have a glass of water and then I have another glass filled with any other different liquid you can think of, ethanol, let's say, and then you count the molecules of ethanol versus water in the same volume, they're going to be totally different, okay? Because it depends on how tightly packed the molecules are, etc. Well, it doesn't matter the identity of a gas because gas particles are so far away from each other. Okay, there's so much space in between them that the actual identity of the gas particles is not going to affect the spacing between them. And that's because we'll get into more of that later, but that has to do with intermolecular attractions between particles. Gas molecules essentially don't feel the effect of each other. They have minimal to no intermolecular attractions. So Avogadro's law is intuitive too, right? If you have a gas in a certain size container and you put in more gas, that volume's going to increase, right? Assuming it's a flexible container wall, right? So it makes intuitive sense. One thing I want to point out, because you'll be practicing a lot of these, is that you can present Avogadro's law in the format I just showed on the previous slide, or you can flip it upside down, right? If it makes your math easier, these are equivalent relationships or equivalent expressions. Okay, so you can put a moles on top or volume on top, makes no difference. All right, last one of this PowerPoint, last of the simple gas laws. Edmontons Law, Used to be called Gay-Lussac's law, but I guess it was inaccurately attributed to Gay-Lussac. So Edmontons Law says it discusses the relationship between pressure and temperature. So basically is saying that the ratio of pressure and temperature is a constant. And again, that's assuming that the other variables, so that'd be number of moles and volume, don't change throughout the procedure. Now, I'm going to point something out here. I see how you hold number of moles constant, right? Just keep extra gas away from it. How do you hold volume? I also see how you hold pressure constant, right? If you do something out in the open at atmospheric pressure, pressure is going to remain constant. But how do you keep volume constant? Okay, so any Edmontons Law are going to have rigid containers, all right, they're made of a material wall that cannot expand and contract. So steel container, glass container with a good seal. So rigid containers when you're dealing with Edmontons Law. Alrighty. All of the simple gas laws that we have talked about, so let's just look at them for a moment. We started with Boyles Law, then we went to Charles' Law, and then we went to Avogadro's Law, and then finally we did Edmontons Law. You can see a pattern in these relationships. And if you combine them so that the three key variables, now moles isn't in here, but the other three are. So three key variables are combined, and ironically, it's called the combined gas law. You get this expression. So there are some problems that you'll run into where it gives you double sets of data on all three variables, pressure, volume, and temperature. And in that case, if you're dealing with three variables, three things that change, you want the combined gas law here, okay, rather than the individual one. So here's a sample using the combined gas law. And again, the way I go through is I label everything. Okay, so here's my first number. Okay, I'm going to call that P1. And this is going to be V1, and this is going to be T1. Now remember that temperature has to be in Kelvin, so make a note to yourself to convert that. All right, they're asking what is the volume under a different set of conditions, so they're asking what is V2. And here they give you the new pressure, P2. Thankfully, units are the same, and then new temperature. So let's plug in using the three things have changed. They've given us three pieces of information, pressure, volume, and temperature. So that's your flag to what equation you want to use. So looking at the combined gas law, the temperature always goes on the bottom, right? And then plugging in the actual values they gave us. Let's see, here's P1. And then V1, 131 liters. And then over T1, temperature has to be in Kelvin. So I'm going to go ahead and just convert that, plus 273. All right, and so now P2 is 235. They are asking us to solve for V2. And the new temperature is minus 52. And then I need to convert it to Kelvin. So just use, like I said, keep using your common sense. All right, so what are the new conditions? You've lowered the temperature. So what happens when you lower temperature? We're looking for V2, we're looking for new volume. What happens when you lower temperature to the volume, right? Well, volume should decrease because of that too. Okay, another variable is change in addition to temperature. It's pressure. Pressure is much lower at a way high altitude. So let's think about what the effect of pressure is. As pressure goes down, what happens to volume? Well, pressure and volume are inversely related. So if pressure goes down, that's going to cause volume to go up. So we have conflicting effects, right? The lower temperature should make volume go down, but the lower pressure should have the opposite effect. So let's see what happens when we work out a sample problem. First of all, converting both of the temperatures to Kelvin, and then plugging all the values in the combined gas law and rearranging to solve for V2, we get that it's 336 liters. Let's compare that to the original volume. Okay, so the volume went up. So what affected it more? Okay, we changed both temperature, we decreased temperature, and we also changed pressure, atmospheric pressure. So what had the largest effect? Means that pressure had a larger effect than temperature. Okay, that's not always going to be the case. That's just the case here. Here's a good summary slide of the simple gas laws. And then the combined gas law. So none of these are hard, but the wording can get tricky. So go ahead and start working a bunch of the practice problems uploaded and get real comfortable with all of them.